Okay, so it's a pleasure to have Professor Hernandez again. This fifth and final lecture of this series.
Thank you. Yesterday we have discussed several things. So one thing that was this family of representation that I denoted by WKAI. So these are what are called Kirillov-Reshetnikhin modules. So these are some simple finite dimensional representations of UQ and G. So it's not all simple, a distinguished class of simple modules, parameterized by a node of the Dynkin diagram of G, of the underlying finite dimensional Lie algebra, a positive integer and a complex number. So which generalize for all types these evaluation modules that we had for SL2. Okay, so we have seen that they satisfy a closed system of relations, the T systems. So their class in the quantum ring satisfy a T system. And then, so it was one thing. And then I explained that by just looking this relation and expecting these are some exchange relation in cluster algebra. It's possible to define some quiver. So now I will state the theorem. So I explained that we define some quiver gamma. So it depends on G, the Lie algebra, and its vertex set Vg is a subset of 1n times T. We started with this whole set, and then I explained that the quiver has two connected components. And we pick up one of them. So this is a set. And here, just to as a reminder, that's a picture I have given already yesterday. So this is a quiver for type A3. I, Z, 1, 0, and 2, and so on, with the arrow. There is the general rule that I have written on the board yesterday. And for B2, so we could write the same column, but then there would be some crossing of arrows. So if you, nicer way to do is to do like this. But if you write G2, for example, then you need a 3D thing. You do not want any arrow. Anyway, so for all types, you have this explicit quiver. So we have, so for the moment, we have a distinguished class of modules, some relations, and some quiver, so some cluster algebra, but we do not have a category yet. So I have to define some category which will handle all this picture. So first we define certain subcategories. C. So C is a category of all finite dimensional modules. So first, there is a category that we call CZ, which the idea is to keep only spectral parameters that are power of Q, to have some kind of discrete family of generators. So the way it's written, it's a category of objects in C, whose composition factors meaning the Jordan-Holder composition factors, the terms that appear in the, yes? That's the set. Vertex set of the quiver. Just to distinguish, the quiver has the arrow in addition. This is just a subset of this. So for example, here, this is a collection of all these couples. For SL2? Yes, good question. So for SL2, so I is just equal to 1. So that's a simple module with a Dirichlet polynomial, which is 1 minus Z q minus 2, 1 minus z q minus 2k minus 1. But this is also equal to an evaluation module from the highest weight module of highest weight k omega 1. And it should be evaluated, there is a here, and evaluated at a, or maybe some shifts. Okay, so now I want to define my category, and I will require that composition factors are of the form so that a simple module that is defined by a Drinfeld polynomials, and it's a collection of polynomials. And we suppose that the condition is that the roots, so I will write it like this, so roots pi multiply, sorry, yes, multiply by, so it should be, yes, pi. They are of the form q minus r minus the I with I r and v. So I assume that the roots of the Drinfeld polynomials, they satisfy some condition. And the condition is that the root is computed as the power of q, and the power is controlled by this set here. So for example, for FL2, the roots are in this case just q minus 4, q minus 2. The condition. Okay, so why do we look at this category? So some remark. So first, this category is monoidal, so that's a statement. It's stable by tensor products, monoidal. That's a fact. There is something to be proved, but it's defined slightly differently as previously. Previously, I said, let's pick up a subring of the Grothendieck ring and look at the modules whose class is in the subring. So it's stable by tensor product by definition. Here we have specified a collection of simple modules, so a subgroup of the Grothendieck ring. And the statement is that this subgroup is in fact a subring. But it's true. Second point is that any simple module in this category can be written as a tensor product of representation in this category up to some automorphism by spectral parameter. So if we understand combinatorially this category, then we understand all simple modules. Okay, so the description of simples. So it implies it's some kind of reduction of this large category to some kind of discrete, at least category, which is generated by a discrete set of fundamental modules. Yes. No, there will be in a few minutes. At this step, there is no reason. Well, maybe for G2 you may have some, but okay. So we want to describe this category. So this category is a bit large. So let's slice this. So. So we will look at certain subcategory. So fix some integer. And so the idea is simple. So here we have this quiver, which is infinite in both directions. And we will just take a slice, so cut, and get rid of some infinite part upstairs and downstairs. So let's write it this way. So let's fix L and let CL, this is a subcategory of CZ. So we keep the same definition. The same definition. But there is a restriction here, and then it will play a role. So with so IR, which is in VL, so VL is a subset. I will give, so I'm precise so that I can state a precise theorem in V. And there is the condition that minus 2L minus 1 should be lower than R plus the I. And here we have broken the symmetry, but maybe up to shift we could. So that's the same definition as Z. But the condition on the roots of the Drinfeld polynomial is restricted. So that means we allow only a finite number of roots. So now examples. So first, we recover the category C1 that I have explained for SL2 and SL3 in my previous talk. Okay, so for G, so an L equal 1, that's the category C1 from above. Last remark before giving examples. So what I explain here is true. In fact, if we understand the all simple modules in all category CL, then we understand all simple modules, because any simple modules in this category CZ for L large enough is in one of this category. So here we could write CL for any L. It's enough to understand this category to understand all simple modules. Okay, so that's a first example. So let me give another example for type B2. So this is SO5, I think, type B2. And L equal 2. So if you look at the condition, it means that we only take this subquiver. So for B2, you have the very big quiver here. So maybe I can write it here. No, I will write it again. So you allow 2 minus 2, 1 minus 2, 1. And 2 minus 6, 1 minus 6. So if you apply this rule to this type B2, you get only 6 vertices. So it's a quiver with 6 vertices. And then, so this is V2. Okay. And so now what we will do is we will define a quiver by keeping arrows between these vertices. Okay, so we can, we have some arrows like this. So this is the subquiver from this large quiver here. So let's give a name to this. So let's gamma L. So it's a subquiver. Subquiver of So obtained by removing all vertices that are not in VL. Obtained by all vertices not in VL. Okay, but we will also freeze some vertices. So precisely here, we will freeze 3 of them. So the extremal one, so the one which is at the bottom for each column. Okay. So we take this quiver, we cut, and we freeze. So let me write it. So, and IR is freezed. What if the condition if R minus DI is strictly lower than minus 2n minus 1? That's the condition. Okay. So in fact, for SL2 and SL3, we get the quiver also that they have defined previously. Okay. C1 with the correct frozen variable. Okay, so now I can state my theorem. Theorem I wanted to state. So we have a category, a quiver, a set of simple classes. Of course, everything has been built to fit together, but so the theorem is the following. So it's true for any type of G, for any G. So there is a ring isomorphism. So between the Grothendieck ring of this category CL that we have defined, and the cluster algebra attached to this quiver with a frozen variable. That's the first statement. Moreover, we can define explicitly an initial seed, and the initial seed is built from Kirillov-Reshetnikhin module. So phi. So here you have, by the IR, I denote the initial cluster variables corresponding to the couple IR. Okay. So here, Z1, 2, Z1 minus 2, and 1. So there are some initial cluster variables. And these cluster variables, through this isomorphism, corresponds to an explicit Kirillov-Reshetnikhin module. So the spectral parameter R plus the I, and here there is some M which is explicit. So if there are questions, I can explain, but it's a bit type dependent. So this is an initial seed whose all cluster variables corresponds to one of these modules that I have described. So this is a large generalization what I explained for SL2. Right? We had this line and all these evaluation modules, the example that I given. So moreover, so here, these are some particular Kirillov-Reshetnikhin modules in this category. There are more, but sorry? It's Q, or maybe I used RI or DI, yes. Q, so this is just, so this Kirillov-Reshetnikhin module, they depend on a vertex of the Denikin diagram, a positive integer, on a complex number. So here, this complex number is q to the power r plus the I, and r is the coordinate of the cluster variable. Oh, but there are many bits of notation, so I understand. So for each cluster variables, it has a coordinate here on this quiver. So it gives you a vertex of the linking diagram, an integer. From this, you build a spectral parameter, a complex number. You have the I and some integer with some formula. This gives the Kirillov-Reshetniki modules. Let's assign. So first, in fact, these are algebraically independent, which is not the true for all Kirillov-Reshetniki modules, but this special collection is. You may define a ring isomorphism like this. This is an isomorphism, and moreover, all other Kirillov modules of these forms, there are many here, are all some cluster variables, some mutation. So all are modules in the N are cluster variables. So that statement. Okay. So maybe I can. Yes, maybe I can make it slightly more explicit for B2. So that's I come to this point in a minute. So example. B2 L equal to. So take this quiver here. So we assign a Kirillov-Reshetniki module for its vertex. And if you follow this rule, so here you have W Q minus 1 to W 2 W. So you have to pick up 6 of them. And okay, so here you have frozen variables. And then, in fact, this one is relatively easy example because it's of type A3. If you forget about the frozen variables, that's A3 quiver. So the category C2 here of the Lie algebra attached to B2 is of type finite type A3. So we know that there are 12 prime modules in this category. 12 cluster variables. Because there are three frozen. So, and so this is the initial seed. And any simple module in this category can be factorized into these 12 cluster variables with a combinatorial rule given by the cluster structure. So this, 2 days ago, I explained this general factorization of simple module for UQ LSM2, and, which motivates the cluster interpretation. And now we go a bit in the reverse way. So we do not really understand very well this category, but thanks to this framework, we find some kind of factorization of the same flavor for other types, because we relate to the same combinatorics. So in this, for example, for this, so that's the simplest non-trivial case, I think, for non-simplized algebra. Yeah. Okay. Any question? Well, it's a cluster algebra of finite type A3. So it's known that there is a parametrization of cluster variable by almost positive roots, I think. And so you get this picture here. But it will be, yeah, so that's some point, it will be controlled by the cluster algebra of type A3. So symmetric type. Also, we are in type B2. So there are things like this, so at first, maybe we could expect that the cluster structure would be related to skew symmetrizable matrix to define cluster algebra, but in fact, it's really ordinary quiver. Sorry, so I wrote that all Kirillov-Reshetikhin modules, which are in this category CL, so there are much more than this specific one, are cluster variables. No. Come back to this. No. But we can also say that all first step mutation are one of these T systems. Starting from this, if you mutate at any vertex of the quiver, you have an exchange relation, and this is a T system. So this is how the quiver is built. Okay, so now the cluster monomials. So after doing this, so yeah. Yes, so you may write for D4, so it will be quite. So if you want to write for D4, you will have to add another column and then connect it to this one. Yeah. Okay. I don't know. Well, so then, okay, so then so this is theorem from 2015. And then we conjecture that, in fact, all cluster monomials are simple classes. That's a conjecture, which in fact is now a theorem, as I will explain. So we conjecture that so phi and cluster monomial two are simple. So of course, there are much more cluster variables than Kirillov-Reshetikhin modules. These are some specific ones. So we could prove it for Kirillov-Reshetikhin modules, but because we know some specific information on the structure of the category, again, these T systems I discussed, which give some control. But then that's another question to get all cluster variables, all cluster monomials. So it is now proved, and so it was first proved by so in this form by Fan Shin in 2017. So using so this is for type AD. So using methods that exist for type ADE based on geometric representation theory, quiver varieties, that in fact, for the moment, are not known to extend to non-simply layered types. And so much more recently, 24, there is a complete proof by Kashiwara, Kimho, for all types. By completely different method. Their methods, in fact, goes back to maybe the examples that I gave at the beginning. So they go back to R matrices. So if you remember the first example I gave, the defect of braiding, and the fact that it gives rise some relations. And so they could, in fact, establish that here all exchange relations come from such degenerated breeding. And so taking advantage of this, they could prove inductively, starting from the initial state, that all simple modules are cluster variables, because they could identify exchange relation coming from some morphism in the category, degeneration of the breeding. So that's the idea. Sorry? No, so they do not, no. So they had the first proof using quivaric algebra, but which could not handle all types. And it's particular type C. Some part of the category of Cassie, as far as I understand, you cannot reach completely through generalized Chauvet duality. And none of the proof is purely in terms of quantum affine algebra. And this is required if you want to. So there are developments about monoidal categorification for quivaric algebra, but that some very I cannot discuss everything here. Okay, but that's not a finished story. So yeah, I would like to say about something more, and maybe you may ask, what about infinite quiver? So here in all this, we took a slice, and we may wonder what happens if we maybe just take half of it, something like this. So let's see. So I will start. I will explain with an example. So my question is, what about infinite? That in fact we have in this picture. So let's look at the example of SL2 first. So recall. So I first recall the finite quiver that we have this finite quiver. So that's the quiver for the category CL. So this is what I denoted G. L, level L that we have discussed previously. So this corresponds to, so if we take, so we have already discussed that this cluster algebra admits a monoidal categorification, which is this category CL or SL2. Okay, which in fact is as the ring generated by the fundamental modules V1 of 1, V1 2 minus 2, up to V1 2 minus 2. That's something we have discussed on Wednesday, I think. Okay, so that's the first thing. So now the first thing we would like to do is to expand to infinity, to get rid of the frozen variable. And here, it's very natural things to do, and it works well. We can take all fundamental modules below. So let's take gamma SL2. And this is what we denote by minus here. So means that we take semi-infinite quiver like this. So it's a semi-infinite. And so it's from this result, it's not very difficult to see that a consequence of this theorem. If you look at the cluster algebra corresponding to this. So this is a monoidal categorification that you get by taking all simples here. R. This is a monoidal categorification. It corresponds to a category E minus Z. So C minus Z, which is defined here, but is defined for all types, just by cutting upstairs, but not downstairs. Okay, so now you would be tempted to say that if we go to the infinity upstairs, you would get the wall thing, and this is not exactly what happens. So if we want, so we have to do something different, but which is similar, but it will be also semi-infinite, but with different orientation. So now we go to infinite quiver. There was this question of quivers with different orientations that are mutation equivalent, but if we go to infinite quiver, it's less clear, not true in general. So for this one, we can do this. So we take this quiver like this. We take also this semi-infinite quiver, but we change orientation at each step. And so we can define an initial seed here. So here we take the Dirichlet polynomial 1 minus z. Here 1 minus z, 1 minus z, q minus 2. So this is what we would do for the category C1. But then for the next one, we go upstairs. So we take L 1 minus z, q2, 1 minus z. And then we go back again. And so on. So if you do this, then you define, in fact, monoidal categorification. So an isomorphism between this botanic ring and the cluster algebra attached to this semi-infinite quiver without frozen variable with this initial seed. So let's say gamma tilde minus to distinguish with this linear one. So this also follows from the combinatorics of LSL2 that I have explained, and it can be extended to general types. But what about the linear quiver, which is infinite in both directions? And to define a monoidal categorification, we have to go to take different algebras, which are called shifted quantum affine algebras. This is what I would like to discuss in the remaining minutes. Well, if you take here, so there are two ways. Categorically, it's clear. At the level of gross-tonic rings, it's clear. So now if you look at the cluster algebra, you have to handle cluster algebra of infinite ranks, so meaning with infinite seeds. So that might be complicated. But for this question, if you pick up a cluster variable here, then you may find a finite number of mutations so that it appears here. So, so there is a subtle notion of inclusion of cluster algebra that was already discussed. But in this infinite rank, you do not require necessarily that any cluster here is a cluster here. So it's enough to say that any cluster variables is a cluster variable. So maybe you cannot build the complete seed here, but individually, each cluster variable will appear. So this is what happens. But you cannot go back, because this category is larger. So there are this thing that all cluster variables are here. It's not a reversible phenomenon. So we had a lot of trouble understanding this kind of mutation process that cannot go. It's related to infinite mutations, sequence of mutations. No. So this is an example to illustrate. No, this you can do for all types. This is in the same KK OP paper. Using the same, changing the. But so what I want to discuss now is something different. Is for the really linear quiver in both directions. So what about this infinite quiver. And so, there is a solution. So how much time? Yes, let's be brief. So we can use a relatively new object, which are called shifted quantum groups. So we can use shifted quantum affine algebras. So these shifted quantum affine algebras, there are variations of quantum affine algebras depending on some additional parameter, shift parameter, variations. QLG. They depend on a shift, mu, and what is mu? It is a co-weight, so a weight of the Lagrange dual algebra, depending on mu, co-weight. For mu equals 0, we recover this one, but it's a much larger families of algebras, were defined a few years ago by Finkelberg and Symbaliuk, following an idea of Boris Feikin in the paper. And so now we may want to look at the representation of this algebra, which gives rise to a larger categories of representation. Because this one is just one individual object here. Okay, so let me explain why it's relevant to this problem. So in fact, each of these algebra has a representation, a category of representation. So each has a category O, analog of the category O for Cas-Moody algebra or quantum groups, but we denote by O mu, and a category of representation. Possibly infinite dimensional module, and which contains a category of finite dimensional module. Okay, so individually, each of these shifted algebra are not quantum groups in the sense that they do not have a coproduct. But if we take all of them simultaneously, it's possible to define a ring structure on the sum of Grothendieck group. I will explain. So each Grothendieck group, so it has no known ring structure. But in fact, I could find a process to define a ring structure on the sum of them. So in all co-weights, so that's what I forget here, that we call O. So that's the category for all shifted quantum groups, and it contains the one corresponding to finite dimensional modules. So these are rings. So are rings have a ring structure. No, of the simple finite dimensional Lie algebra. So for SL2, for example, that's just an integer. So they have ring structure. So, and then we can, so as above, define some category, some kind of discrete subcategories. So, which contains our category. So maybe I do not explain the details, but we can classify simple modules here. And instead of being parameterized by polynomials, as finite dimensional modules, they are parameterized by rational fractions. That's different. But then we can ask to integrability condition on the roots, as we did. So impose that the roots or the poles of rational fraction are powers of Q, as we did here, to define certain category. Okay, so this is defined by a restriction on simple constituents, simple composition factors. So I go a bit fast, but in fact, I explained this 2 years ago in the same room. So you may have a look at the YouTube. But so at the time and there are some progress in them, so that I want to explain. So yes, so let me first state a theorem. From 23. So the theorem is the following: is that if you take this category of finite dimensional modules of all shifted quantum groups, then it is isomorphic to a cluster algebra corresponding to the whole quiver. So this is gamma G without any restriction. So for SL2, for example, we get this infinite quiver. Okay, and moreover, the initial seed is formed of one-dimensional representations. That's something quite different. That this algebra, they have a continuous family of one-dimensional representations that are not isomorphic one to each other. Something you do not see from usual loop algebra or usual B theory, but here there is. So the initial seed are all one-dimensional. Then it's easy to see that the tensor product of them are still irreducible because all tensor products are one-dimensional. But so it's slightly easier to write than the previous theorem here in some sense. And moreover, it is we can say that cluster monomials are tend to so that's it. So the other are tend to certain simple classes. And this second part relies a lot on the theorem of KKOP, crucial ingredient of the proof. Okay, so good, but now that we have this category O, we may wonder, is this also has some cluster structure? And this is what happens. That's a good question. In fact, no. So for SL2, they all come from the same. So these one-dimensional modules, they come for a shift, which is a fundamental coweight, fundamental weights of the Lagrange dual Lie algebra. So this algebra has a family of one-dimensional simple modules parameterized by C star. And so on each column, so for SL2, the initial seed is, so these modules, there are usually, these are what we call pre-fundamental modules. In some sense, there are more fundamental than fundamental ones. They play the role of fundamental modules in this category. But there are some, as there are already fundamental modules here, we call them pre-fundamentals. And the initial seed for SL2, you just put L11, L1, Q2, L1, Q minus 2. Like this. And that's it. You take your one-dimensional modulus, and you just shift the spectral parameter. Then you can do mutation, and you get representation of higher dimension, of course. The initial seed is this one. Okay, so good. So now I want to discuss this category here. And so that's the theorem that I had explained at this conference 2 years ago. At the time, it was work in progress. So now it's published. So it's joint work with guys, myself, and Leclerc. So the theorem, published theorem, is for type ADE, but now I can give. So we define a quiver. We define an explicit quiver. Okay, gamma G prime, so that you have the same. So K0 is isomorphic to this cluster algebra. So to be correct here, we have to define certain completion of the cluster algebra to allow some infinite sum of cluster variables. That's a technical detail. So let me give the example of SL2. So for SL2, this quiver it's also infinite linear quiver, but with a different orientation. So we take infinitely many arrows in this direction, and there is one vertex which is reversed. This is what we found. So you may say it looks the same as linear, but this quiver has a symmetry property, because if you mutate here or here, it will just translate the reversed arrow. So you can mutate here, 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 and then the reverse arrow will go down. And if you do infinitely many times, you will go back to the linear quiver. So that's how we can understand the fact that this contains strictly this category by this. But you need some infinite number of mutations to do this. So this is the quiver for SL3. For SL2, maybe I can write it for SL3, because it's always a bit of this form. There's some kind of regular part, and some more complicated part in the middle. So for SL2, we just reverse the arrow. So I can maybe just write quickly that we get for SL3. So it's like this. There are some quadrilaters which appear here that we have not seen for the moment. Okay, and that should be up. Here, okay. And then up. So it is also, so this is for SL3. It's some infinite quiver. Upstairs, you recognize the one with the triangles that we have discussed for SL3. Below also. And then you have 4 quadrilaterion. So that's the analog of this perturbation for SL3. So then it gets more complicated for general ADE type, but we could find it. And in fact, we are now finishing a paper for non-simply lace type, where we also have the quiver. So it gives something about this category, but however, now you may ask about cluster monomials. And in this case, this is a conjecture. Now the conjecture is that so cluster monomials. So we could prove this for SL2. It's already not completely trivial for SL2, so you have to work in the category, but it's okay for SL2. But as far as I know, it's open for SL3, for example, this question. But following all this, we have many evidences to support this, and there are in fact examples of cluster variables that do not come from the initial seeds that we know that are simple modules. So there are many evidences for this. So yes, I will stop here.
Any questions, remarks?
No, we did not use R matrices here. And in fact, in general, there are no known R matrices for shifted quantum affine algebras. So that's what?
For the coproduct.
There is a Drinfeld coproduct. Already there is only one coproduct. So still, yes, there are many tools that we have for ordinary quantum affine algebra that we do not have yet, maybe, in this general statement. So still, it seems that the structure of the quantum rings has many similarities to what we are familiar, but many open questions.
One point you said the description of simples in CZ implies that of C, but
yes.
Can you say what does it mean?
Oh, yeah, it's just if you take an arbitrary simple modules, let's take all roots of all Drinfeld polynomials. We group them by orbit for the action of Z multiplication by Q. So you get orbits. And then the simple modules will be isomorphic to the tensor product of simples corresponding to each orbit.
So
some kind of Steinberg theorem.
Can be written as tensor product of shifts of simple modules from CZ.
Exactly. And this factorization is easy to write. Then what is more complicated is how each factors, and then you have the combinatorics of cluster algebras coming into the game.
Any other questions? If not, then let's thank David once more. I want to convey the thanks of the organizers and all of us, the audience, to all the three speakers. In spite of their busy schedules, they have taken time out to come here and lecture. Thank you so much.